starting on the notes where it talks about percent yield, the first thing that it lists is theoretical yield. And your theoretical yield is going to be the calculated amount of product that can be produced from a given amount of reactant. So we're going to write calculated. So if something is calculated, it is going to be considered your theoretical yield. This is determined mathematically. Using stoichiometry calculations. And then your actual yield is the amount of product that you actually produced when you carry out the chemical reaction in lab. So if you have a word problem like the one below, and it says in lab you burned this much and you produced this much, that would be your actual yield. And so you don't physically have to be the one doing the lab, but of course what you get as your value during lab will be your actual yield.
What's the difference between theoretical and actual?
Theoretical means that you calculated it mathematically. So you used stoichiometry to calculate how much of something you should have been able to produce. And then actual is what truly happens, like in real life.
So is the theoretical one, will it ever like match up to the actual one?
No, that's why we have what we call percent yield, which is the ratio of the two things. Hardly ever will it end up being exactly 100%. So the percent yield is the ratio of the actual yield to the, that's ugly, sorry, actual to the theoretical yield expressed as a percent. This is different. So a lot of students in my earlier classes were saying that we already learned this last semester, but this is different. What we learned before was percent error, which was when you take the actual value, so we did use actual as something, the actual value of something or the accepted value of something minus your experimental value of something. So we did the density lab with that one, where you calculated the density of a known metal like copper or zinc or something like that, and then you had to look up in your chart what the accepted value of that metal was, and then you calculated how far off you were from the real thing. It's a similar concept in the sense that we're still calculating a percent and there is a lab component to it, but this one is different because your theoretical yield comes from calculating how much should be produced using math. So example 1 kind of starts us off nice and easy. What I want to point out is that the actual yield and the theoretical yield are both talking about products. This is always going to be something that is produced. So yield means produced. So when you are dealing with percent yield, you are never going to be calculating a number regarding the reactant. So your reactant will be your starting information, and that's how you find your theoretical yield. But both of these are talking about products only. So example 1 says, in lab, you burned 3.2 grams of magnesium, and you produced 4.8 grams of magnesium oxide according to the given reaction. So if I'm looking at this reaction down here, this means that I start with 3.2 grams of magnesium, and I make 4.8 grams of magnesium oxide. Let's take a little step back and balance the equation. So the coefficients would be just 2, 1, 2 to balance this one. So the reaction that is taking place is you're burning magnesium in lab, and you were given actual values for both of these. This is actual because it's what happened in lab. This is not considered an actual yield because even though this is the amount of reactant I had in lab, it is not a yield at all. It's a reactant. Do you see how I got that? And then it says your calculations showed that you should have been able to produce or should have been able to make 5.3 grams of magnesium oxide. So if you should have been able to make that based on your calculations, that yield would be called what? Perfect. The way that you get that value, So this one has already been done for you, but normally I would have you calculate it yourself. But the way that we would calculate this is by starting with a given amount of reactant and determining how much of that specific product I should be able to make. So here that's already been done just so that we could do our first one and understand the process of calculating the percent using this formula. So if I take my 4.8 grams of magnesium from right here, because that is my actual yield of magnesium, I'm going to divide that by my theoretical yield of magnesium, which is 5.3, and then I multiply that by 100 just to turn it into a percentage. So using your calculator, type this in. So I have 4.8 divided by 5.3. And then most of you, when you see this number, you can turn that into a percentage. That's just fine. If you can't turn that into a percentage in your mind, just multiply by 100. That's why I put that on there. So then you end up with 90.566 as your percent. So I would write that in this case, I was able to yield 90.566? 90.566% of what I should have been able to produce. So in percent yield, you cannot actually produce more than 100% of what it says you can produce. However, sometimes, in like the lab we're going to do on Monday, you might calculate that you did get over 100% yield. But because we know the law of conservation of mass says that's not possible, like what that would be telling you is that you created matter somehow. So this is similar to back if you think when we did our separation lab, if you didn't dry your product out all the way, if you didn't wait for it to completely dry, if you didn't boil out all the water, if you didn't wait long enough in the drying oven, you could calculate that you got over 100% yield, but you need to understand that that is not actually physically possible to yield over 100% of what it should have been. Does that make sense? Okay. So this number, I just rather do an arbitrary number of decimals, but of course we need to take into account sig figs. So each of these has 2 significant figures. This should have 2 significant figures. So I would round this to just 91% yield. Did I do it wrong? Did someone say wait? Okay. If you have questions, you can feel free to ask your questions. So when I tried to scare you into not talking, that was so that you weren't interrupting, but questions are always good. All right, example 2 says, during a lab experiment, 24.8 grams of calcium carbonate is decomposed and 13.1 grams of calcium oxide is produced. So I'm going to start with 24.8 grams of this calcium carbonate. And then I produce 13.1 grams of calcium oxide. My equation is already balanced. I have 1 calcium, 1 carbon, and 3 oxygens. I have 1 calcium, 1 carbon, and 1, 2, 3 oxygens. So everybody's balanced. Our coefficients would all just be 1s. What is the actual yield in this example of calcium oxide? Do we have enough information to determine the actual yield? I just didn't hear if someone answered.
Oh, is it yes? We have enough information, right?
Yes, we have enough information.
Right.
So what is it?
What's the answer?
Mm-hmm.
13.
Yes, 13.1, because remember that actual yield is just talking about what happens in lab. So if you see that key phrase in lab, that is hinting that that is actual yield. So in this, it tells me during a lab experiment, this was decomposed, and this is what I got. So 13.1 would be my answer. 13.1 grams of calcium oxide is my actual yield. Then the theoretical yield was not given to me, but I can calculate the theoretical yield. You won't use your actual yield to calculate theoretical. You need to use the given amount of reactant. So what the theoretical yield actually means, or truly means, so I'm not using the same word a bunch of times, the theoretical yield means that if I start with this amount of reactant, how much of that product should I have been able to make? So what actually happened is I made 13.1 grams, but that doesn't mean that that is what I could have calculated. So I'm going to start with this as my given information. So I'm going to plug in 24.8 grams of CaCO3. And then I use the entire stoichiometric process to determine how much of this I should have been able to make. And when I say how much of it, it should be in the same unit that your actual yield is in. So if I'm going to plug them both into the same equation, sometimes I guess we could technically give you moles for actual yield, and then you would calculate theoretical in moles as well. But in most cases, and in this case, we'll give you grams as your actual yield, which means you need to take this, your stoichiometric problem, into grams of CaO. So I'm going to make this equal something grams CaO. So if I'm starting in grams of CaCO3, again, I start with this because this is the given amount of reactant. And so what we're answering is if I have this much reactant to start, how much product should be able to form? I would bring down grams of CaCO3 and put moles of CaCO3 on the top. Between grams and moles of CaCO3, we call that conversion factor molar mass, which is always just 1 mole. And then the number of grams would come from our periodic table, so I would calculate the molar mass of CaCO3. Oops. So calcium has a molar mass of 40.08. And then I would add to that the molar mass of carbon, which is 12.011. And then I would add to that the molar mass of oxygen, but I would multiply that by 3, so 3 times 15.999. So you can go ahead and plug that into your calculator. This is just to get our molar mass taken care of right away. So 40.08 plus 12.011 plus, and then I'm going to do open parentheses, 3 times.
And Nolan, put positive for checkout, please.
Yes, ma'am.
Thank you.
Thank you. So I calculated the molar mass of 100.088. So I'm going to go back to my chart and plug in 100.088 grams of CaCO3. Then I continue in my chart, so that would cancel out grams of CaCO3. I need to bring moles of CaCO3 down to the bottom. And from moles of CaCO3, I can go into moles of the substance that I'm actually interested in, which is CaO. And then moles of CaO would come down to the bottom so that that cancels out, and I would put grams of CaO at the top. Between moles and moles, the ratio is just 1 to 1 because all of my coefficients would be 1s. And then moles of CaO to grams is molar mass again. So 1 mole of calcium oxide is going to be, I'll just pull up the calculator. And come back here. We're using the same things, but it's not the same ratio. 40.08 as my molar mass of calcium plus 15.999, so 56.079. Is that what you got?
Yes.
If it's not, chime in, let me know.
Yes, it is.
Okay, thank you. Then we just solve it. So we go all the way across, multiplying everything on top and then dividing by everything on bottom. Pick up your calculators and actually do this with me so that you are getting practice typing this in. So I'm going to start with 24.8. You don't need to type the ones in, so you don't have to multiply by 1, divide by 1, because those will not change your answer at all. So 24.8 times 56.079. Then I divide by 100.088. And I think that's it. And then I hit enter. And I calculated 13.895 something. 13.89536. And then I write the wrong thing. 13.89536. So I write down a whole bunch of decimals, but then I look at the very end to see my significant figures. This has 3 sig figs, so I'm going to make my answer match 3 sig figs. So zooming in to right on the line, if it will go. 13.89 would just round to 13.9 grams of calcium oxide. This number represents the theoretical yield. Of CaO. So this might be I'm sorry, I guess I could have said this at the beginning. I did my theoretical yield down here just because I had space. Is that why you were confused when I was calculating? The percent yield is calculated using the equation that we have up here. So now that I have my theoretical yield of 13.9 and I have my actual yield of 13.1, that is answering the question for letter C, which is percent yield. So percent yield is 13.1 divided by 13.9. It matters which one you have on top versus on bottom, and then you'll multiply that by 100. So 13.1 divided by 13.9 is 0.94, but then when you multiply by 100, 94.24. 94.24. I only have 3 sig figs here, so I'm going to make this match 3 sig figs as well. So I will change that to 94.2% yield. So answer to letter C. I know this is kind of all scratchy and all over the place, but that is my percent yield. This one was my theoretical yield. So it is calculating the theoretical yield that takes the most work. Once you get that, just using the equation up here is pretty straightforward. Questions on any of that so far? So the reason that you can't do any calculations early for your lab is because you are going to measure approximately 0.3 grams of one of your reactants, but you're not probably going to get exactly 0.3 grams when you actually go to measure it in lab. So what you are going to write down is your exact mass of the reactant that you start with, and then you're going to use your specific mass to calculate your theoretical yield. So unless the amount of reactant that you measure is exactly equal to the amount of reactant that somebody else measured, your theoretical yield will not match another lab group's. Do you see why? Okay, so that's giving you your given information, and then you calculate it at the end there. Let's do example 3. So this one is already balanced for us. If you look at the equation, it says during a lab experiment, 1.87 grams of aluminum reacts with an excess of copper 2 sulfate. So now we have context for that word excess. Excess just means we're not going to run out of it. There's going to be copper 2 sulfate left at the end. Actually, this is exactly the... Never mind. During lab experiment, this much reacts with an excess of that. And 4.65 grams of copper is produced. What is the percent yield? So if you get overwhelmed with word problems, or you lose track, or you can't figure out what you're looking for, I always like to label it on the actual reaction so that I can see what's going on. So as I read the question, during a lab experiment, 1.87 grams of aluminum. So I'm going to put 1.87 grams right here, just to help me keep that straight. That tells me that I am starting with a reactant of aluminum that weighs 1.87 grams. That's probably going to be my given information, but let's keep reading. Reacts with an excess of copper 2 sulfate. So you can put like a little infinity sign by this if you really want to. That just means you're not going to run out of it, and it means that you won't use that in any of your calculations. So what is running out in this case is aluminum. You can tell that by the way that the question is worded. And then it says 4.65 grams of copper is produced. So I find copper on my product side, and this is 4.65 grams. And then the question is asking, what is the percent yield? Do I have a value given to me for theoretical yield?
The 4.65.
The 4.65 represents what? The actual yield. So if you start to get these things confused, label them. So this is your actual yield, which will be the numerator when we actually go to calculate percent yield. I do not have a value given to me for theoretical yield. So to calculate that, I use the given amount of my reactant to determine how much, given this much reactant, how much copper should I have been able to produce. So I'm going to scroll this way just so that I have space to write it all. I'm going to say 1.87 grams of aluminum. So don't get this confused. Even though 1.87 grams of aluminum is what you actually started with during lab, that does not mean that that is your actual yield, because 1.87 grams of aluminum is a reactant and it is not a product. Therefore, it is not your yield. You will use that to help you calculate your theoretical yield. So based on this amount of aluminum, I'm going to bring grams of aluminum to the bottom and moles of aluminum to the top. Let's just set up the whole thing first, and then we'll go back and calculate molar mass. So I'll bring moles of aluminum to the bottom. How come? How do I know I'm going to bring that down? Yes. What does that do? Is it helping me at all to bring it down? Yes, because it will cancel it out. Thank you. Okay, so moles of aluminum, and then from moles of aluminum, you can go to moles of anything else in your entire equation. In this case, we are interested in copper, so I'm going to go to moles of copper. Then I bring down moles of copper again. The reason we know we're not stopping in moles of copper is because our actual yield was given to us in grams, so I need to get my theoretical yield in grams of copper as well so that I can compare the same unit to the same unit. So then I put grams of copper. And then once I have that figured out, I will have something grams of copper as my answer. What? We're trying to find the grams of copper because we are given the actual yield of copper. And so I guess it should probably say what is the percent yield of copper specifically, but that is the product that we have actual yield for. Does that help? Does that answer your question? What do you mean?
Or is it just gonna be what is the percent?
I don't know. What does it say? I think.
For the test, it's gonna be labeled. Can you label it?
Percent yield of copper, you mean?
Yeah.
Yeah, sure. Okay, so between moles of aluminum and grams of aluminum, our conversion factor is called what? Grams to moles. Molar mass, which is always 1 mole. Since I'm looking at aluminum as my substance, aluminum is directly on the periodic table, so the molar mass is just 26.982. So I'm going to plug that in right here. And then I have moles of copper to moles of aluminum. That comes from my mole ratio, which is in the balanced chemical equation. The number of moles of copper is 3 for every 2 moles of aluminum. And then grams to moles, again, that's still called molar mass, which means I'm putting 1 mole, because molar mass, by definition, is always 1 mole. And the number of grams of copper comes from my periodic table, so 63.546. Oops. 63.546. And then let's calculate this. even if you have not been plugging this into your calculator so far, please pick up a calculator right now and practice typing this in. This is another one of the ones that has multiple non-1 values on the bottom, which means you need to divide by both of these. So 1.87 times 3 times 63.546. Then I hit equals, and then I'm going to hit divided by 26.982. Then I hit the division sign again, so I hit divided by 2. And then when I hit enter, I got this. Is that what you calculated? So you can get the same answer even if you use parentheses, put parentheses on the entire numerator, put the parentheses on the entire denominator, but if you do that, then you multiply the denominator instead of hit divide. You just hit divide at the end of the top one, like this. All right, 6.60612. 6.60612. And so I have 3 sig figs. I'm going to round this to 3 sig figs, so 1, 2, 3. If you cut it off when you write it at 6.60, that is not correct rounding. The answer is 6.61 because the 6 right here would round that up to 1. So this value that we just calculated, why did we go through that effort? Good. And then to calculate my percent yield, this is why I don't think it's that big of a deal if it's not specifically labeled what you're looking for, but I'll go through on the test and make sure that it has what you're looking for the percent yield of. But if you only have the actual yield for one thing and you only need to calculate the theoretical yield for one thing, it's going to be obvious that the percent yield that you're calculating is of that same thing. So 4.65 divided by 6.61, and then you multiply that by 100 to give you your percent yield. So 4.65 divided by 6.61 equals this times 100. So 70.3479. So when I round this to 3 sig figs, this is going to just say 70.3%. So this means that whenever this person, whoever is doing the lab in this case, whenever they conducted their lab experiment, they were only able to recover 70.3% of the copper that they said that they were going to be able to get. You see how it works in context? Sure. All right, let's do one more. I'll give you guys time to practice this one by yourself. I can help you get set up. So, example 4 says, an ore of antimony, which is Sb2S3, reacts with an excess of iron according to the given reaction. If 15 grams of Sb2S3 reacts and the percent yield of this, of Sb is 91.5%, what is the mass of Sb? What mass of Sb is actually produced? So, this one is kind of working backwards a little bit because you are given the percent yield. So again, if you get overwhelmed with the word problems and you don't know where to start labeling on your reaction the information that you're given. I know that it reacts with an excess iron or excess of iron. So I'm going to do the same thing I did in the equation above and just put a little infinity symbol above here to show that that is not going to run out, which even though it's not necessarily relevant to this question, I know that Sb2S3 is my limiting reactant. If 15 grams of that, so 15 grams, reacts and the percent yield is this, I need to figure out the mass that is actually produced. So if I start with percent yield, which is actual over theoretical, is equal to 91.5%. So if I write that, it's going to be 0.915. So you see how I set that up? Then you just start plugging in the information that you have. So if I have 15 grams, wait a second, actually produced, blah, 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 blah. Oh, we are trying to find the actual. We don't have the theoretical yet, but I have this information, which if you look at my previous two questions is how you calculated your theoretical. So you can use this information, your 15 grams, to calculate theoretical yield. So 15 grams of SB2S3. So take that and convert that into your theoretical yield. And it's going to be theoretical yield of this, since that is what the question gave you information on. So I'm going to pause there real quick, give you time to set this up and work through it. I will come and help you as needed.